I'm going to start with a question that I got in a couple of emails, and it's about the Chinese remainder theorem. So let's just go back to the Chinese remainder theorem. We were looking at things like this. We were looking at equalities of the form x equals a mod m and x equals b mod n, where m and n were relatively prime. And we said that if we have this system of equations and a and b are some given constants, then we have a unique solution modulo n times n. Okay. Now, I got 2 emails asking me why this is unique. Now, one way of arguing that this is unique is to just go back at the algorithm that we had for finding the answer here. So we had an algorithm for finding a particular number that gives these remainders. And just showing that the algorithm finds all the solutions and it finds one solution. That's a valid proof for saying that something is unique. But I'm going to give you an easier proof. So this is what we want to prove. This is our theorem. We want to say for every n, m, a, b, where n and m are relatively prime, there is exactly one number x in the set 0, 1 to nm minus 1. So I'm doing it modulo nm, such that basically x satisfies these 2 requirements, such that x is equal to a modulo my first number, and x is equal to b modulo my second. And by the way, I'm doing this with 2 equalities here. Of course, you can do it with any number of equalities because that's just how we prove the general case of the Chinese remainder theorem. We just add induction to it. Okay, so for the existence part, we already have an algorithm that finds an x. So we know that such an x exists. I want to show that it's unique. Now, here's what I'm going to do. Look, my algorithm is going to take a and b, and it's going to give me an x, right? So I can think of my algorithm as a function. So I have a function f. Let's say this is my algorithm, which basically takes a and b and maps it to the correct x. Okay, but what is this function? What is the type of this function? What is a? A is a number between 0 to m minus 1. Okay, so I have 0, 1 to m minus 1. That's the domain of A. What is B? B is just a number between 0 to n minus 1. Okay, and I'm mapping to what? I'm mapping to numbers from 0 to nm minus 1. So how many elements do I have on this side? N times m. How many elements do I have on this side? Also n times m. Right. And is it possible that 2 elements on the left-hand side are mapped to the same element on the right-hand side? No. Because if I have something like A1, B1, and also A2, B2, both of them mapped to the same x. What does that mean? That means that if I look at x modulo m, it's both A1 and A2, right? Which doesn't make sense if A1 and A2 are not the same. Okay, so I have n times m different values on the left-hand side, and my algorithm is also 1 to 1. But I also have n times m values on the right-hand side. So it has to be on 2 as well. So it's a 1 to 1 correspondence. Okay. Great. So I have one solution and exactly one solution. Great. Now we're going to move to the main topic of today, which is Fermat's little theorem. Now, this is something that I asked you to prove in the problem set, and we're going to do it now. And we're going to see many different proofs. Now, this is one of the most important theorems we're going to work with. And it's actually important that you understand all of the proofs and you understand the ideas and intuitions behind all of them. So what is the theorem itself? The theorem says this. It says, if A is not a multiple of P, then A to the power of P minus 1 is congruent to 1 modulo P. And of course, when I write P, I mean a prime number. So for every prime number P, I have this. So if I take any number that is not a multiple of P, that is not 0 modulo P, and I raise it to the power of P minus 1, that would be 1 when I'm calculating things modulo P. Okay. Now, why is this the case? Here's the first proof, and this is the proof that I was asking you to come up with in the problem set. So consider some number A, and let's say I define a function f sub A, and what this function does is that it takes any number x, and it just maps it to x times A. Okay. And all of my calculations are modulo P here. So all of my numbers are between 0 to P minus 1. X is between 0 to P minus 1. X times A is between 0 to P minus 1. Okay. So I'm considering this function. First of all, is this function a permutation? So is it 1-to-1 and onto? Is it a 1-to-1 correspondence? Yes. Okay. Why is it a 1-to-1 correspondence? Because basically A is relatively prime to P. And P is a prime number, so anything that is not 0 modulo P is relatively prime to P. Okay. And so this means that if x times A is equal to y times A, I can cancel the A from the two sides, if this is modulo P. Right. Okay. And why is it, so this shows that it's 1-to-1. Why is it onto? Because suppose I have some number y. Okay. I want to solve this. I want to solve x times A equals y modulo P. Okay. But I know that A has a modular multiplicative inverse because GCD of A and P is 1. So I have an A inverse, right? So if I just take y times A inverse times A, that's going to be y. So I can just set x to be this. Okay. So basically, if I consider this function, the function that maps every number to that number times A, this is going to give me a permutation. And we've seen before that whenever we have a permutation graph, and a permutation graph is always a bunch of cycles, bunch of disjoint cycles. Okay, let's create some examples of these cycles. And because I'm too lazy to do it on my own, I'm going to code it. I couldn't install C++ here. I don't know anything about Windows. Okay, so let's say I have some maximum n. This is a horrible keyboard. Okay. Here's what I want to do. I want to create the cycles of this permutation. So I want to read a number P and a number A, and then I want to basically write all of the cycles of this permutation. So I'm going to do something like this. So I'm going to say for every I from 0 to P. So here's what I'm going to do. I'm going to go over all the numbers. And I'm going to say, if I haven't seen this number before, let's find the cycle containing this number and print it. Okay, and then I keep going until I get to a number that I haven't seen in any of my cycles. Okay, so I say, if this I was not seen before, then for J that starts from I, and I have to go as long as I haven't seen J, and every time I multiply J by A, and I take its remainder modulo p. So for every j like this, I'm going to write j, and I'm going to say I've seen j. And let's say after every I just print an end line so that I know this is the end of my cycle. I think this is running. So let's say 11 and 2. Okay, I didn't put any spaces. Let's run this again. 11 and 2. So if my prime number p is 11 and my number a is 2, I actually get only 2 cycles. One cycle is the cycle that only contains 0. So of course, 0 times a is 0. And I'm always going to have this cycle, right? That cycle is always there, no matter what p and a is. I'm going to always have a cycle that looks like this. This is just 0 on its own, because 0 times a is always 0. And in this case, I also have this other cycle, 1, 2, 4, 8, 5, 10, so on. So 1, 2, 4, 8, 5, 10. 9, 7, 3, 6. So in this case, this is a cycle of length 10, right? So I have that A is 2 and P is 11. So in this case, I got a cycle of length 10. But what is this cycle? This is basically just saying A squared, A to the power of 3, so on. And this is a cycle of length 10. So this one at the end is actually A to the power of 10. Right. So 2 to the power of 10 is congruent to 1 modulo 11. This is just, of course, an example. We want to prove it for every A and for every P. Okay. Now, if I were always this lucky, if I could just guarantee that I would always get 2 cycles, one cycle containing 0 and the other cycle of length p minus 1, I would be super happy, right? Because I would then have this cycle of length p minus 1, which means that a to the power of p minus 1 is right before a, which means that a to the power of p minus 1 is 1, right? But this doesn't always happen. Let me see if I can find an example where this doesn't happen. I guess if I do 11 and 3, yes. You see, if I have 11 and 3, now other than the trivial cycle of 0, I have 2 other cycles. So let's draw this as well. So in this case, A is 3 and P is again 11. I have the trivial cycle from 0 to itself. I have 1, 3, 9, 5, 4. And then I have 2, 6, 7, 10, 8. Now, in this case, I'm happy too. Because, look, if you look at the length of this cycle, the length of this cycle is 5. So this means that if I look at the powers of A to the power of 5 is 1, right? So A to the power of 5 is 1. That means A to the power of 10 is also 1, because that's just A to the power of 5 times itself. It's 1 times 1 is 1, right? So as long as the length of these cycles is a divisor of p minus 1, I would be happy, right? I don't need to have just one cycle. All I need is to say, let's look at this main cycle, the cycle that starts with 1. If its length is a divisor of p minus 1, then I know that I can take a to the power of p minus 1, and that would be 1, because that would just be starting here, going p minus 1 steps around the cycle. But if the length of the cycle is a divisor of p minus 1, I will end up where I started. Okay. Now, why is the length of this cycle always a divisor of p minus 1? Yes. So other than this trivial cycle, and again, we don't care about this trivial cycle at all the other cycles are the same size. Why is that? It's because I can just look at the smallest element in 2 cycles. Okay. So in this case, the smallest element of my first cycle is 1. The smallest element of my second cycle is 2. But what does this tell you? This tells you that the first element here is 1 times A, right? The second element is 1 times, sorry, the first element is 1. The second element is 1 times A. Then I have 1 times A squared. All of these, of course, modulo P. Then 1 times A cubed, so on. But what do I have here? I start with 2, then I have 2 times A, 2 times A squared, 2 times A cubed, and so on. Okay, so the elements in the second cycle are just twice the elements in the first cycle. Right? And in general, if, let's say my first cycle always starts with 1, let's say the second cycle starts with some number b, right? Whenever I have some x in the first cycle, I always have b times x in the second cycle. Right? Okay. Does this mean the cycles are the same size? Yes, because b is also relatively prime to p. So if I have b times x is equal to b times y, I can cancel the b's, right? So I can say this for all of my cycles. So no matter how many cycles I have, all of them are the same size. So the size of my cycles, whatever it is, has to be a divisor of p minus 1. Because other than 0, I have p minus 1 other numbers, and they're divided into a bunch of cycles of the same size. Right? So especially I care about this first cycle, and the size of this first cycle is a divisor of p minus 1. So what is a to the power of p minus 1? It's just start in the first cycle from 1 and go p minus 1 steps. But the length of the cycle is a divisor of p minus 1, so you end up back at 1. And this proves that a to the power of p minus 1 is always congruent to 1 modulo p. Okay. So this is the proof that I like the most because I prefer graph theory. But let me now give you a different proof of the same theorem. So again, this is our theorem. This time I'm going to do something else. This time I'm going to look at all the multiples of A. So remember, we previously had a different kind of cycle where in every step we added A, right? So this was a multiplicative cycle where I'm multiplying my number by A every time. But before this, we've already seen an additive cycle. So let's look at the additive cycle of A. So let's look at the cycle that starts like this. Goes A, 2A, 3A, so on, until it comes back. Okay. What are the elements in this cycle? So these are all the multiples of A, right? So I have A, I have 2 times A, I have 3 times A, so on to p minus 1 times A. And I have all of them because, again, A and P are relatively prime. So multiples of A create all the possible remainders modulo P. Okay. But what does that mean? I have P minus 1 possible remainders modulo P, and all of them are in this cycle. So this set, the set A, 2A, 3A, so on, is the same as the set 1, 2, 3 to P minus 1. Right? Not in the same order, but in some order. Okay. Again, let's look at a simple example. Let's say P is 5, and let's say A is 4. Okay. I'm going to start with 4. 4 plus 4 is 8. That's 3 modulo 5. 3 plus 4 is 7, which is what? Modulo 5, 2 modulo 5. Then 2 plus 4 is 6, which is 1 modulo 5. And 1 plus 4 is 5, which is 0 modulo 5. And then 0 plus 4 is 5. So if you look here, I have all the possible remainders. I don't have them in the same order. I don't have it as like 0, 1, 2, 0. I forgot to write 0 here. Okay. Oh, but no, that's fine because I've forgotten it on both sides. Yeah, you can add 0 to both sets, or you can not have it. Anyway, I'm going to get all the remainders modulo P, but I'm not going to get them in the same order. I'm going to get them in some other order. But who cares? As a set, these two sets are the same, right? And again, all of our calculations are modulo P. So when I say two numbers are the same, I just mean that they're congruent modulo P. Okay, so if these two sets are the same, I can just multiply all the elements in each of the sets, and I should get the same result. So this means that if I take A times 2A times 3A, so on, to P minus 1A. This is the same as 1 times 2 times 3, so on, to P minus 1. Okay. Now we have a better way of writing this. This is, of course, P minus 1 factorial. Right. And what is this side? Yeah, this is A to the power of P minus 1 times P minus 1 factorial. Can I cancel the P minus 1 factorial from both sides? Yes, because P minus 1 factorial is relatively prime to P. It's the product of numbers from 1 to P minus 1. It doesn't have P in it, right? So I can cancel the P minus 1 factorial from both sides, and I just get that A to the power of P minus 1 is congruent to 1 modulo P. Okay, so this is our second proof for Fermat's little theorem. I'm going to give you a third proof. Okay. The third proof is actually, oh, I know it better. So the third proof is a bit unexpected. Because it's a proof by induction. I want to prove this by induction on A. How does that work? So let's say proof by induction on A. First of all, you agree that I only have to prove this for A's that are between 0 and P minus 1, right? So I'm not really considering any other cases. But in any case, let's just prove it for every A. Let's say I'm doing proof by induction on A. I have to do a base case. And for your base case, you can choose 0 or 1. Let's just do both. So if A is 0, what is A to the power of P minus 1? Well, actually, you cannot do 0. Sorry, I forgot that I've written the Fermat's little theorem like this. I've said P does not divide A. Okay, so base case is when A is 1. So 1 to the power of anything is 1. So of course, A to the power of P minus 1 is 1 modulo P. Base case is very true. Okay. Now, suppose that I'm looking at A plus 1 to the power of P minus 1. what can I do here? You know what? I'm not very happy with this because I want my base case to also work for 0. So let me just rewrite Fermat's little theorem in a different way. I don't want to have that special case. So instead, I can write it like this. I can say that for every prime p and every integer a, we have a to the power of p is congruent to a modulo p. This is the same thing, right? Because a to the power of p minus 1, if it's 1, then I can just multiply both sides by a. And also, if a and p are relatively prime, then I can divide both sides by a. So it's the same thing, except that now it also works for 0, right? Because now I can say 0 to the power of p is 0. So I'm just writing my theorem in this way so that it also works for 0. Now let's prove this by induction on A. This makes my life easier. So my base case, again, you can use 0 or 1, but let's say if A is 0, then 0 to the power of P is, of course, 0 modulo P. You can also do 1 to the power of P is 1. This is very easy for every prime. Okay, now I want to do my induction step. So I want to look at A plus 1 to the power of P. But what is this? We've had the binomial theorem. We know how we can expand this, right? So this is A to the power of P plus P choose 1, A to the power of P minus 1, right? Plus P choose 2, A to the power of P minus 2. So on to P choose P minus 1, A, and then plus 1. It's actually P choose P times 1, but P choose P is just 1. Here's what I'm going to claim. I claim that all of these terms, except the first one and the last one, are multiples of P. Okay. So this is my claim. I want to say that if K is bigger than 1 and less than P, then P choose K is a multiple of P. So it's equal to 0 mod P. Okay. Now, I'm going to come back to this claim, but just believe me for now. If this claim holds, what am I saying? I'm saying this is a multiple of P. I mean, in this case, this is just P, right? This one is a multiple of P, and so on. All of these are multiples of P. So if I'm doing calculation modulo P, I can just ignore everything that comes here. So I have this. I have A plus 1 to the power of P is just equal to A to the power of P plus 1 when I'm doing calculations mod P, right? Okay, but what is A to the power of P? By induction hypothesis, it's just A. Okay, so this is A plus 1 modulo P, which is exactly what I wanted. Okay. So as long as I can prove my claim here, then I have a new proof of the Fermat's little theorem. Okay, so why does this claim hold? Let's come back here and let's call it a lemma now because I want to give it a proof. Okay, why does this lemma hold? What is P choose K? We had a formula for P choose K. It's just P factorial over K factorial times P minus K factorial. let's simplify this part and this part. So I want to cancel this and this, but I can't cancel it exactly, right? So I will have a bunch of things remaining. I will have P times P minus 1, so on to P minus K plus 1, right? If I cancel the P factorial with P minus K factorial. And then I have K factorial down there. Okay. Now, I want to claim that this is a multiple of P. Now, why is this a multiple of P? I have a P up here. I don't have a P down here, right? So just look at the factorization, the prime factorization of the number here. It definitely has a P in it. If you look at the prime factorization of K factorial, these are all numbers that are smaller than K. I'm multiplying them together. It doesn't have a P in its prime factorization. So whatever this result is, it's going to have a P in its prime factorization, so it's a multiple of P. Okay, great. So now that we have this lemma, which is 0 P, now our proof is complete. And we proved by induction that for every prime number P and every integer A to the power of P is equal to A1. Oh, every non-negative integer, right? But that's fine. You can just, because you only need to prove it for the numbers between 0 and P minus 1, and then it's proven for everything else. But the induction is only for every non-negative integer. Okay. Great. So now we have 3 different proofs of Fermat's little theorem. But what's the point? Well, again, when it comes to calculations, this will help us. So remember that we constantly were thinking about how to calculate A to the power of B modulo C, right? And we had this really nice algorithm where we said that basically we find A to the power of B over 2, multiply it by itself, and so on. So we need logarithmically many steps. Okay, we had fast modular exponentiation. But now, suppose that I want to compute, suppose I want A to the power of B modulo some prime number P. What do I know? I know that A to the power of P minus 1, and again, here, let's say that P doesn't divide it. A to the power of P minus 1 is 1, right? Modulo P. Which means that if I multiply this by itself, I'm just multiplying 1 by 1. So A to the power of 2 times P minus 1 is also 1 modulo P. A to the power of any number times P minus 1 is 1 modulo P. Okay. This is, again, going through that cycle. If I just go through the cycle many times, I'm going to always end up at the same place. It doesn't really matter. Right. So this means that if I want to find A to the power of B modulo P, I don't really care about my number B, no matter how big it is. I just care about B modulo P minus 1. Okay. So this is my theorem. If B is the same as, let's say, C modulo P minus 1, then A to the B is the same as A to the C modulo P. Right? And I don't need to give you a proof. I just gave you the proof. So this is now kind of a faster algorithm for modular exponentiation. Because when I want to find A to the power of B modulo P, I can first make B much smaller. I can make sure that B is at most P minus 1. Right, so I just take the remainder of B modulo P minus 1. And then I calculate A to the power of that remainder using the same algorithm that I had. Okay. But now the next question is, well, this worked for prime numbers. Fermat's little theorem worked for prime numbers. What breaks if my number p is not a prime? So what if instead of doing all of the calculations modulo some prime number p, I'm doing calculations modulo some composite number n? What breaks then? Well, the thing that breaks is actually this idea that all of our cycles, except the trivial cycle, are the same size. Now, where did our proof come from when we said that all of our cycles are the same size? I said, look at the smallest number in the second cycle, suppose that that's b, then for every number in the first cycle, I have b times that number in the second cycle. So in this case, b is 2, so my second cycle just contains twice every number in the first cycle, right? But I was assuming that these will all be different. So if I have different numbers here, and if I multiply each of them by 2, I will get different numbers here. But how did I get that? I got that because 2 was relatively prime to my prime number. Okay, so it doesn't really have to do with the number a itself. My proof had to do with the smallest number that appears in some other cycle being relatively prime to p. And that doesn't happen in general. So my problem is that if I'm working with some natural number n, let's say a composite number n, I cannot say that. Maybe I have whatever, let's say I have 10 numbers in my first cycle, but when I multiply the numbers by some other number by 2, I get only 5 different answers. Right? That's possible. Okay. So how can we get around this? The way we can get around this is that we should only work with the numbers that are relatively prime to our modulus. So if I could say that all the numbers are relatively prime to whatever modulus I'm using, other than 0, of course, 0 is always a special case. If I could say every other number is relatively prime to my modulus, then I wouldn't have a problem. But that only works for prime numbers p. But for other numbers, I'm going to just define the set of numbers that are relatively prime to this modulus n. So here's what I'm going to do. I'm going to say, let n be a natural number. And actually, whatever, let's say, let's n greater than or equal to 2. Actually, let me see, do I need it to be greater than or equal to 2? No, I can do it with 1, 2. Let n be greater than or equal to 1. I'm going to define a number called phi of n. We define phi of n as the number of numbers between 1 and n that are relatively prime to n. Okay. So this is what I do. I look at all the numbers a that are between 1 and n and relatively prime to n. And I ask how many of these numbers do I have? So it's the size of this set. Okay. And this is called Euler's totient function. By the way, this word has no meaning at all. You can check the meaning of this word. In Latin, it means something like as many as, something like that. It doesn't mean anything. Just call it totient. That's what it is. Mathematicians are not good at naming. Okay. So Euler's totient function takes a natural number n and maps it to the numbers between 1 and n, to the number of numbers between 1 and n that are relatively prime to n. So for example, if I want to find phi of 6, I can look at all the numbers that are smaller than 6, and I can just count how many of them are relatively prime to 6. So 1 is relatively prime to 6, 2 is not relatively prime to 6, 3 is not relatively prime, 4 is not relatively prime, 5 is relatively prime to 6, 6 is not relatively prime to itself, right? So phi of 6 is 2. Great. Now we're going to study this function because we want to use this function to somehow get an extension of Fermat's little theorem. Okay. So how are we going to study this function? What is the value of this function? So here's what I claim. So this is my theorem. I'm saying, look at the prime factorization of n. So let's say that n is p1 to the power of alpha 1, p2 to the power of alpha 2, so on to pk to the power of alpha k. And let's say that all of these powers are non-negative, of course. I mean, I'm not going to include zeros in there. Okay. Where are the alpha i's are at least 1. Okay. I claim this. I claim that phi of n is n times 1 minus 1 over p1 times 1 minus 1 over p2, so on to 1 minus 1 over pk. Now, my intuition here is this. I'm saying, look at all the numbers from 1 to n. Okay. What proportion of these numbers don't have p1 in their factorization? Well, 1 minus 1 over p1 of them, right? Because n over p1 of these numbers are multiples of p1. And then what proportion of the remaining numbers are not multiples of p2? 1 minus 1 over p2, and so on. So that's the intuition we have here. So basically, we're going to take the prime factorization of n, and if the prime numbers that appear there are p1 to pk, then I'm going to say take n and multiply it by this, 1 minus 1 over p1, 1 minus 1 over p2, so on. But of course, this is very hand-wavy. We have to actually prove it. Okay. So I'm going to give you two kind of different proofs. They're not really different. They're based on the same ideas, but let's go on. So let's do proof number 1. I'm first going to consider a special case where all of my prime numbers are appearing with a power of 1. So suppose n is just p1 times p2, so on to pk. I want to show that in this case, the theorem holds. Okay. Now, again, the intuition is the same as before. I want to say that if I look at all of my numbers, how many of them are multiples of p1? How many of them are multiples of p2, and so on? But here's the thing. From the Chinese remainder theorem, I know this. I know that if I have x equals to, let's say, a1 modulo p1, and x equals to a2 modulo p2, so on to x equals to ak modulo pk. I know that this has a unique solution modulo n, right? So if I give you some values a1, a2 to ak, and I say I want x to be a1 modulo p1, to be a2 modulo p2, and so on, there is a unique solution modulo p1 times p2 to pk, because all of these are relatively prime to each other, of course. These are just prime numbers, literally, right? So what is a1? A1 is basically the remainder of this number x when I divide it by p1. A2 is the remainder when I divide it by p2, and so on. So I know that whatever values I choose for a1 to ak, I have exactly one solution. Okay, and not only I have exactly one solution, I have exactly one solution in the range of 1 to n, because the range of 1 to n gives me all the remainders modulo n, right? Okay, but when is a number relatively prime to n? A number is relatively prime to n if it's not a multiple of any of my pi's, right? So it means that if I want to get a number that is relatively prime to n, I have to make sure that A1 is not 0, A2 is not 0, so on, AK is not 0. So any choice that I make for A1 to AK, as long as I don't put any of them as 0, would give me a number X between 1 and n, which is relatively prime to n. And vice versa, it's a one-to-one correspondence. Very easy to see. Okay, so the number of numbers that are relatively prime to n, phi of n, is the number of ways that I can choose A1 to AK here such that none of them are 0. So how many choices do I have for A1? P1 minus 1. How many choices do I have for A2? P2 minus 1. So on to PK minus 1. Okay. So this is P of n. And now it's a simple algebraic manipulation to see this is the same as this, right? So I can write it like this. I can write it. So I have P1 minus 1 here. I can write this as P1 times 1 minus 1 over P1, right? And then I can write this second one as P2 times 1 minus 1 over P2. And so on to PK times 1 minus 1 over PK. And now if I multiply all the P1 to PKs, I get n, and then the remaining thing is exactly what I wanted. Okay, so we proved the theorem for the special case where every prime appeared with a unit power. But now let's say that it doesn't appear with a unit power. So let's say that n is something like this. N is P1 to the power of alpha 1, P2 to the power of alpha 2, so on to Pk to the power of alpha k. Just remove the extra powers that you don't need. So just define n prime to be P1 times P2, so on to Pk. Okay. Now, a number is relatively prime to n prime if and only if it's relatively prime to n, because they have the same prime factors. Right. So here's the thing. I look at all the numbers from 1 to n. Sorry, to n prime. How many numbers in this range are relatively prime to n prime? Phi of n prime. Right. Now let's look at n prime plus 1 to 2n prime. How many numbers here are relatively prime to n prime? Again, these are just shifts of these. So again, I have phi of n prime numbers here that are relatively prime to n prime. Right? And I can do this. I can keep going. And let's say that I say k is n over n prime. So I just have k copies of this thing. Right? So I will go until I have k minus 1 n prime plus 1 to k n prime. And here I have phi of n prime numbers in this range that are relatively prime to n prime. Okay. But again, the numbers that are relatively prime to n prime are the same as the numbers that are relatively prime to n. Okay. So how many numbers in here are relatively prime to n? Just k times phi of n prime. So I just proved that phi of n is k times phi of n prime. And what was k? K was just n over n prime. So this is just n over n prime. And what was phi of n prime? It was n prime times 1 minus 1 over P1, 1 minus 1 over P2, so on to 1 minus 1 over Pk. So this cancels with this. I get exactly what happens. Okay. Great. So this was our first proof. Now I'm going to give you a second proof. This is the second proof. And the reason I like this second proof is that it gives you a lemma, which is actually quite useful. So we start with this lemma. We say that the Euler's totient function is multiplicative. And what that means is this. It means that if n and m are relatively prime, then phi of nm is equal to phi of n times phi of m. Okay. So whenever a function has this property, so I mean, instead of phi, just put f, we say that it's a multiplicative function. So this is just saying that phi is multiplicative. Why is this the case? Do you have an intuition for this? Yeah, so this is again the Chinese remainder theorem, right? So I'm looking at all the numbers from 1 to nm. Okay. I can look at the remainder modulo n and modulo m. I can say, let's say x is equal to a modulo n and x is equal to b modulo m. We know that for any possible value of a and b, we have exactly one solution modulo nm, which means that we have exactly one solution between 1 and nm, right? But which solutions do I want? I want the GCD of whatever number I'm taking, this x. I want to count the number of x's such that GCD of x and nm is 1. But what does that mean? That means that the GCD of x and n should be 1, and the GCD of x and m should be 1. These are the same things, right? So GCD of x and nm is 1 if and only if GCD of xn is 1 and GCD of xm is 1. Now to see this, just look at the prime factorization again, right? When I say GCD of x and nm is 1, that just means that x and nm don't share any prime factors, right? But that's the same as saying x doesn't have any shared prime factors with n, and x also doesn't have any shared prime factors with n, right? So if I want GCD of x and nm to be 1, I have to choose a here such that a is relatively prime to n. And I have to choose b here such that b is relatively prime to m. And then that would give me an x that is relatively prime to nm. And again, this is if and only if, so it gives me exactly those x's. So the question is, in how many ways can I choose a and b such that a is relatively prime to n and b is relatively prime to m? Well, I have phi of n ways to choose a, and I have phi of m ways to choose b. So phi of nm is phi of n times phi of. Okay. Should I do it again? Okay. Look, I want to find all the x's between 1 and nm that are relatively prime to nm, right? So I want x to be relatively prime to nm. What does that mean? That means that the GCD of x and nm should be 1, which we said it's the same as GCD of xn is 1 and GCD of xm is 1. Okay. So, but from the Chinese remainder theorem, I know that for any value of a and b that I choose here, there is exactly one x in this range such that x is equal to a modulo n and x is equal to b modulo n, right? And so any x that I take here gives me a pair a and b. Any a and b that I pick here gives me back the x. It's a one-to-one correspondence, right? So if I pick an x here that is relatively prime to nm, I will get an a here that is relatively prime to n. And I will get a b that is relatively prime to m. because of this, right? Vice versa, if I take an A that is relatively prime to N and a B that is relatively prime to M, then I have this. So I have that GCD of X and NM is going to be 1. Okay, so if I want to pick exactly those X's that are relatively prime to NM, I have to pick exactly those A's that are relatively prime to N and exactly those B's that are relatively prime to N. Okay, what is the number of X's in this range that are relatively prime to NM? By definition, that's phi of NM. In how many ways can I choose A? I have to choose an A that is relatively prime to N, so phi of N. In how many ways can I choose B? Again, it has to be relatively prime to M, so phi of N. So phi of NM is phi of N times phi of N. Okay. So we start here, but remember, I'm doing this lemma because I want to go back and give another proof for this theorem. So the second part of my proof is that, again, I look at a specific type of N. So in the previous proof, I looked at N's that looked like this. Now I'm going to look at a different type of N. So this is, let me just put this in the box. This is the end of that theorem. So I want to say this. I want to say consider an N that is of this form. That is just some prime number P to some power, to the power. So just consider the natural numbers N that have only one prime factor. Okay. What is phi of N? So if I take any other number, its GCD with N is either going to be 1 or it's going to be some power of P. So if I look at all the numbers from 1 to N, if there is any number here, let's say P, 2P, so on, that has P in it, its GCD with N is not going to be 1. But if it doesn't have a factor of P, then the GCD with N is going to be 1. So how many numbers here are multiples of P? N over P, right? So how many numbers are not multiples of P? N minus N over P. Okay. Which is, again, the same as N times 1 minus 1 over P. Okay. Now, I know that if I have a number that is just some prime number to the power of alpha, this is the number of, and this is its totient value, basically, phi of N, right? And I also know that if I have two numbers that are relatively prime, phi of NM is phi of N times phi of M. So in general, I have my general case. And my general case is this. N is, let's say, P1 to the power of alpha 1, P2 to the power of alpha 2, so on to Pk to the power of alpha k. I say take each part separately. So let's say N1 is P1 to the power of alpha 1. N2 is P2 to the power of alpha 2, so on. And Nk is Pk to the power of alpha k. So what is phi of N1? It's just N1 times 1 minus 1 over P1. Phi of N2, again, N2 times 1 minus 1 over P2, so on. And phi of Nk is Nk times 1 minus 1 over Pk. But here's the thing. All of these numbers are relatively prime to each other. Any pair of them are relatively prime. Because I have different prime numbers here, right? So P1, P2 to Pk are not the same. So if I take the phi of product of N1 to Nk, that's just the product of the phis. So phi of N1 times N2 times Nk, which is just N, is going to be the product of the phis. But that's just N1 times N2 all the way to Nk, which is N, times 1 minus 1 over P1, 1 minus 1 over P2, so on to 1 minus 1 over P. Okay. Great. So we proved this in two ways. You can choose which proof you like better. The important thing is that if you have the prime factorization of a number, you can easily find Euler's torsion function. Okay. Now, why did we care about all of these things? Because now I want to give another theorem, and this is Euler's theorem. This is an extension of Fermat's little theorem. So in Fermat's little theorem, we were saying that look at a to the power of p minus 1 when p is a prime number, right? Let's go here. Yeah. So I was saying if p is a prime number, a to the power of p minus 1 is congruent to 1 modulo p. But okay, if I have a prime number p, what is phi of p? What is the torsion function of p? It's p minus 1. So this is actually phi of p, right? So that's how I want to extend this. I want to say, look at a to the power of phi of n in general. So this is Euler's theorem. I want to say, let a be relatively prime to n, then a to the power of phi of n is what modulo n? 1. Okay. So this is basically the same as Fermat's little theorem, except that I've now extended it to every number n. N doesn't have to be a prime anymore. But instead of raising it to the power of n minus 1, I'm raising it to the power of phi of n. Okay. Now, why does this hold? Let's again go back to our cycles. Actually, you can take every one of the 3 proofs that I gave you for Fermat's little theorem, and you can extend them to the general case. I'm not going to do it for every one of them. I'm going to do it for the cycles one because I like cycles. So here's the thing. I'm not going to consider all of the numbers. I'm only going to consider the numbers that are less than or equal to n and relatively prime to n. Okay. So let's say I have my set big A. This is the set of all the numbers between 1 and n. By the way, you can also do 0 and n minus 1. I don't care. As long as you take n consecutive numbers, this will work. Okay. So I take all the numbers between 1 and n that are relatively prime to n. Actually, I should use a different notation because a is supposed to mean something there. So all the numbers x between 1 and n such that x is relatively prime to n. I call this set big A. Okay. And now I look at the same function. Remember the function that we had when we were doing Fermat's little theorem was f sub a. But now I consider this a function from a to a, which takes any number x and maps it to x times a. Okay. First of all, why is this a function from a to a? So a is the set of numbers that are relatively prime to n. And we know that this small a is relatively prime to n as well. So if x is relatively prime to n and I multiply it by something else that is relatively prime to n, of course, the result is also relatively prime to n. Again, just look at the prime factorization of the numbers here. Okay, so this is from a to a. Is this a permutation? Is it a one-to-one correspondence, a permutation? Yes. And the reason is exactly the same as in our proof for Fermat's little theorem. Right? So it's one-to-one because if x times a is equal to y times a, you can cancel the a from both sides. Because again, all you needed for being able to cancel n, to cancel a, is that a is relatively prime to n. And also for any number that I give you here, you can just multiply it by the inverse of a, and you get a number here that will map to it. Okay. So this f of a is now going to give me a bunch of cycles. And by the way, I don't have the pesky 0 anymore because 0 is not in A. I've got rid of 0. Right. So I'm going to have a bunch of cycles because, again, this is a permutation. I have one cycle that starts with A, so 1A, A squared, so on. It comes back to 1. And I have a bunch of other cycles. Okay. And now I'm claiming that all of these cycles are the same size. Okay. Now, why are all of these cycles the same size? Oh, what the hell? This is bugging out. Okay. Why are all of these cycles the same size? Because suppose I take some number here, some number B. Let's say it's the smallest number in the second cycle. It doesn't even have to be the smallest number. You can just pick any number. But whatever, I take the smallest number in the second cycle, right? So what is my first cycle? Let's say it's 1A, A squared, so on, to A to the power of K, right? Or actually, let's call it A to the power of K minus 1, and then 1 is the same as A to the power of K. Okay, so let's say this is a cycle of length K. Now, what will I have here? I will have B times A times A squared, so on, to B times A to the power of K minus 1, to again B, which is B times A to the power of K. Okay, so I claim that any number that I have in the first cycle, I have that number times B in the second cycle. And I claim that if I take two different numbers in the first cycle and then multiply them by B, I'm going to get two different numbers in the second cycle. That's actually the important part, right? So let's say I take two numbers here in the first cycle. So let's say I take A to the power of I and A to the power of J, and they're not the same, right? Then if I multiply them by B, this is also not going to be the same, because B is relatively prime to N. I'm only looking at the numbers that are relatively prime to N. And so if these two were equal, I could cancel the B from both sides. Okay. So I really need this property. I really need the property that I'm looking only at the numbers that are relatively prime to N. And because I have this, I can basically say that, well, this cycle is the same length as this cycle, because I have a one-to-one correspondence between my cycles now. Just take any number here, multiply it by B, you get exactly one number here, and vice versa. And you can do this between the first cycle and any other cycle. So all of my cycles have the same length. But what is the total size of all of my cycles? It's just the size of A, which is phi of N, right? That's just by definition. So phi of N is the size of A. So I have a bunch of cycles of the same size. Their total size is phi of N. So the size of one of these cycles, which is K here, should be a divisor of phi of N. Okay. But great, that means that if I take A to the power of phi of N, that means that I'm starting at 1 here, going around this cycle, taking phi of N steps. But phi of N is a multiple of K, so I'm just going several rotations along the cycle and coming back to where I started. So that means that A to the power of phi of N is equal to 1 modulo. Okay. As an exercise, try to extend the other proofs that we've seen for Fermat's little theorem to this case. It's actually quite easy, and it would be maybe some use cases of the Chinese remainder theorem in there as well. So not hard. Okay, I want to prove one more theorem. This is Wilson's theorem. Actually, I have to say this. Wilson didn't actually prove this. Wilson just guessed that this holds, and then I think if I remember correctly, Lagrange proved it. But of course, the British have to take credit for everything, even if the French proved it. So it's called Wilson's theorem now. So it's this. For every prime number P minus 1 factorial is congruent to minus 1 modulo P. First of all, I want you to realize that if we prove this, this is giving us another proof for Fermat's little theorem. Because you can look at my first proof, no, my second proof of Fermat's little theorem, and we had the P minus 1 factorial there. If I have this, I can just replace the P minus 1 factorial with minus 1. Right, I mean, it kind of simplifies it. Great. But why is this the case? Why P minus 1 factorial is minus 1 modulo P? So what is P minus 1 factorial? It's just multiplying all the numbers. 1 times 2 times 3, so on to P minus 1. But forget about the 1 here, because I mean, 1 doesn't really do anything in multiplication. And forget about the base cases. So forget about the case where P is 2 or 3. So if P is 2, just calculate it, it works. If P is 3, calculate it, it works. So let's say that I only want to prove it when P is at least 5. Okay. So for example, for P5, P minus 1 factorial, which is 4 factorial, is going to be 1 times 2 times 3 times 4. Okay. I want to say that this is minus 1. What do I know here? What happens if I multiply this by itself? What happens if I take 4 factorial squared? Okay, I can forget about the 1. I don't care about the 1. I have 2 times 3 times 4. But these numbers, 2, 3, and 4, they're relatively prime to 5. So each of them has a modular multiplicative inverse modulo 5. So what is the inverse of 2? That's 3, right? Because 2 times 3 is 1, modulo 5. The inverse of 3 is 2. The inverse of 4 is 4 itself. So if I multiply 4 factorial by itself, I'm including every number and its inverse. And every number when multiplied by its inverse is going to give me 1. So this 2 times 3 is going to give me a 1. This 3 times 2 is going to give me a 1. 4 times 4 is going to give me a 1. So P minus 1 factorial squared is 1 modulo P. I can say this in general because I can say, well, forget about 1. Just look at the numbers from 2 to P minus 1. Right? Each one of these numbers has an inverse. And if I multiply all of them together, I get this. Okay. But does this mean that P minus 1 factorial is equal to minus 1? No, because maybe P minus 1 factorial is itself 1. Right? So we kind of got close to proving Wilson's theorem, but not exactly. We still have something remaining. So how would you prove that P minus 1 factorial is actually minus 1? What is minus 1 modulo P? Minus 1 is the same as P minus 1. right? So maybe what I want to prove is that p minus 1 factorial is equal to p minus 1 modulo p, right? I want to use the same idea as here, but this idea wasn't quite there. Like it gave me two possibilities, 1 and minus 1, but it didn't give me that it's exactly minus 1, right? So instead, let's try this. So this is our second attempt. I'm going to say, let's prove p minus 1 factorial is the same as p minus 1 modulo p. But here's the thing. If p minus 1 factorial is the same as p minus 1, I can cancel the p minus 1 on the two sides. So this is the same as proving that p minus 2 factorial is 1 modulo p. Okay. Now, can you use a similar idea as here to prove that p minus 2 factorial is 1? So you see here what I was doing was that I was looking at the numbers from 1 to p minus 1, and I was matching each number to its inverse. But in order to make sure that I have the inverse of every number, I had to include two copies, right? And that's what gave me this bad equality. I mean, I don't hate this equality per se, but it doesn't give me that it's minus 1, right? And the reason it doesn't work is that I have that power 2 there. Okay, so if I could just have one copy instead of two copies, I would be happy here. But if you look at these inverses, when is the inverse of a number equal to itself? It's only p minus 1. And actually, if you had 1, it would also be there, like 1 and p minus 1. So 1 and minus 1 are the numbers where they're inverses of themselves, because 1 times 1 is 1, and minus 1 times minus 1 is also minus 1. It is also 1, sorry, right? So if I didn't have p minus 1, then every number and its inverse would be different. And that's exactly the situation in p minus 2 factorial, right? So I have my numbers. What is p minus 2 factorial? It's 2 times 3. And remember, I'm just proving it for p that is at least 5, right? Times 4, so on, to p minus 2. Right? But each of these numbers has an inverse modulo p minus 1. And this inverse is not the same as this number. Right? So this thing is actually some number a1 times its inverse, times some other number a2 times its inverse, so on to a p minus 2 over 2 times its inverse. So it's 1. And again, all of these calculations are modulo p. So p minus 2 factorial is equal to 1 modulo p. And because p minus 2 factorial is equal to 1 modulo p, then p minus 1 factorial is just this times p minus 1. So it's p minus 1 modulo p. But p minus 1 is the same as minus 1. So p minus 1 factorial is minus 1 modulo p. But this proof is not quite complete. We need one more thing. I had a hand-wavy moment here when I told you that, well, if a number is the same as its inverse, it's either 1 or p minus 1. It's either 1 or minus 1. We have to prove that. Okay, so this is the lemma that we need, is that the only numbers that are their own inverse, the only a's such that, well, if a is its own inverse, what does that mean? That means a squared is 1. A times a is 1. A is its own inverse, such that a squared is 1 modulo p are 1 and minus 1. Okay. But this is quite easy. So here's the thing. Let's say a squared is 1 modulo p. What does this mean? This means that a squared minus 1 is a multiple of p, right? But what is a squared minus 1? Yes, so it's p divides a plus 1 times a minus 1. But this is a prime number. It's dividing the product of two numbers. So it has to divide one of them. So this is the case if and only if p divides a plus 1 or p divides a minus 1, which is the same as saying a is either 1 or minus 1 modulo. So the only numbers that are their own inverse modulo p are 1 and minus 1. And so our proof works.